Okay, so right now मेरी slide दिखा रही है आप लोगों को? Slide is visible? Abhijit?
Yes, sir.
Okay. So this is the another question, that is how do the PID parameters it is affected the system in dynamic control systems. Okay, so we have to know that is PID proportional integral derivative control. It has three various constant terms which is represent that is Kp, that means the proportional control constant part, Ki, that means the integral controller part, and this is Kd, that means the derivative controller part. So using these three constant, that is these three controller parameters, that is Kp, Ki and Kd, it can be summarized in a table. So here you can see these are the basically four major characteristics we have discussed in previous slide, that is rise time, overshoot, and settling time, and steady state error also, that is SS error, that means steady state error. So proportional controller, please remember this table. This table it is very important in our tuning of a PID controller systems also. Okay, so proportional controller, its rise time is always that is decrease, but overshoot it is also increase also, and settling time it is not changes, that is an NT, that means that no defined trend, that means that it is changes slightly or not, so that means it is negligible. So that is NT, that means no definite value or no definite trends any coming in here also, that means minor changes it is here also settling time, but steady state error always decrease in the proportional controller parts also. So that's why we have to use this proportional controller part, okay, in a PID controller part. Then integral part, we have to know if this integral controller part or integral constant terms, its rise time is always decrease also, same as to the proportional controller part. Overshoot it is also increases, but settling time in this integral controller part it is also increase in gradually. Okay, and steady state error we have to calculate in eliminate in this system, that is the integral control systems. Then this is the Kd, that means the derivative controller part, its rise time it is not value is coming, that means the minor changes is coming in this rise time, but overshoot it is always decrease, the derivative controller part its overshoot value it is always decrease also, settling time it is also decreases, and steady state error it is not any value it is changes, that means the minor changes. So this response, proportional controller, integral controller, and derivative controller, we have to use this parameter for a control in industry, that is a PID controller, fine tuning systems also. Okay, so this table it is very important. So please remember these four categories: rise time, overshoot, settling time, and steady state error. Okay, so using this table we have to control the three controller part. So these are the basically typical step for designing of a PID controller part. That means when you have to design or any control system, that is automatic control system, you have to design for the PID controller part. So you have to follow these steps also. First one, determine what characteristics of the system needs to be improved. Okay, that means static or dynamic characteristics you have to first determine. Okay, then number two, used proportional controller, that means Kp, it to decrease the rise time also. Okay, so we have discussed in these tables also, proportional controller and integral controller, it's always rise time it is also decreases. Okay, so number two, use proportional controller, that is kp, decrease the rise time. But number two, that is use kd. Why use in derivative controller in the pid controller part? Because is to reduce the overshoot value and the settling time. So in this pid controller part, we have to use this integral controller to reduce the overshoot error or settling settling time also. Any questions, anyone? And next, use integral part. This integral part, that is ki. Okay, it is uses for the eliminate of
सर
the
हेलो
steady state error. Yes.
सर 2 नंबर में सर जो केपी है सर केपी को सर राइस टाइम क्यों डिक्रीज करेंगे तो उससे क्या सर एडवांटेज?
देखो, राइस टाइम का डेफिनेशन क्या था यहाँ पे? राइस
सर
टाइम का क्या?
90% जो रीच करता है सर फर्स्ट टाइम पे.
Yes, yes. मतलब you have to starting the any plant or system, you have to starting the any proportional controller part. So it is desired timing. That means a little bit timing it is required for the first level to the next level also. So in this between this timing, we have to value is it is 90% we have to deserve in this rising time also. So that means this decrease the timing, starting time is decrease the timing. So this little bit timing we have to decrease this in the rise time systems also. So that's why we have to tell this proportional controller part, this rise time, starting time it is also decreased. Then when you have to continue this process, that means steady state value it is also coming. Okay, that is also slightly also increases. That is it tends to the overshoot value also. Okay, clear? It is clear.
यस सर.
Okay, so using this three controller part, we have to uses in this PID controller part particular operations. First, KP it is decrease the rise time. KD, that is differential controller part, we have to uses the reduce the overshoot value and also settling time also. And integral part we have to uses eliminate the steady state error. So when you have to design any PID controller part in our control action systems, so you have to follow these four categories or four steps also. Next, this is the first method, that is Zigler Nichols tuning method or tuning rules we have to use this in our PID controller part. Okay. So this Zigler Nichols, it is actually this is the two names, that is two scientist names. Okay, scientist Zigler and also Nichols. So both are developed this tuning method in a PID controller systems. It is a basically conducted numerous experiments, and it is proposed rules that determine the value of the proportional controller, integral controller, and derivative controller. It based on the transient step response in a process plant also. So they proposed more than one methods we have to use this in this PID controller part. But in this PID controller part, when we have to use this, it has different types of controller variables, that is controller constants also variables. So it applies to plants with neither integrators and not, that is dominant complex conjugate poles also. So when you have to use a unit step response, okay, in the steady state S-shaped curve, it is also we have to tense its no overshoot value it is coming in this Zigler Nichols method. So in this Zigler Nichols tuning of the control system in the PID controller parts, its output is coming, that is steady state error. It is slightly increases in the overshoot value, but in this S-shape value, it is basically steady state value we have to measure in this graphically method. So in this Zigler Nichols method, here are S-shaped curve always we have to deserve here. Here you can see these are the basically graphical structures. Okay, here you can see these are the steady state value we have to calculate it from here. So these are the first method we have to apply this S-shaped state input impulse curve. Okay, so this is the starting time. Then after few seconds or few timing, this is also changes. Okay, so these are the average value. Okay, in the regions of this constant term of time constant term in the t, then which are determined the drawing a tangent line. This is the basically tangent line and inflection point. This tangent line at the inflection point it of the curve is finding the intersections of the tangent line with the time axis and the steady state level of the line also. So when this input first input we have to calculated from this response of the curve first is saved. So we have to measure first two constant term, that is the one is delay time, that is L. These are the basically delay time, this 0 to this point. Then another constant, that is a time constant, that is a T. This period, this one to this one, this period it is called the time constant. And this tangent line it is determine the inflection point of the curve of the finding of the intersections value of the S-shaped step input response curve. Okay, so this is Zigler Nichols first tuning method we have to use this in our PID controller part. So it has S-shaped curve we have to determine. So it has two constant part. Two constant we have to characterize in this method. First one, that is the delay time, that is L. Another one is the time constant T. And this tangent line which is inflection point to the curve, and it is finding to the intersections of this tangent line. Okay, it is clear all of you?
Yes, sir.
Okay, any others? Only one person is response, that is Abhijit, and another there are lots of people are joining in the class but not response. How many students are available in your department, Abhijit? Strength?
So 35 approx.
35. But attendance is very low. So 17, 18, I'll follow this 17, 18. Maximum 20 students are present day by day classes. But other people are not classes. But it is very important because we have tracked the day by day attendance also. Because those who have attendance is below 75%, so they are suffered for the they are not attending this, that is internal term, internal marks, internal exams also. So these are the basically rules. Okay, so next, these are the basically response tables we have to observe the first method, all of you knowns. These are the different types of controller when you have to use in this Zigler Nichols tuning method. This is KP, all of you know, proportional controller part, TI, which is denoted for the rise time, sorry, reset time, and this reset time it is also integral, it is related to the integral controller part. TD, that means the derivative time, it is related to the derivative controller part. So when we have to use this proportional controller part, it's P controller, only P controller. It has the value Kp, that is T by L. What is T and what is L? I am telling in that first the last slide also. T is the, that is, these are the basically T time constant, and L is the, that is the delay time. Okay, so that is delay time, that is L, and T is the time constant. Its value always T by L. But when you have to use only proportional controller part, it has no value, that is the integral, that is no value. Okay, that means 0 or not mentions here. When you have to use a proportional integral controller part, it has a slightly constant term 0.9. Okay, when you have to solve the mathematical problems, so in your syllabus there are no mathematical examples are not coming, only you have to know the method, that is Zigler Nichols What is the uses of these operative cultures of these Zigler-Nichols tuning methods also. So in this Zigler-Nichols controller part, this proportional integral part, that is proportional constant term 0.9 T by L, and it is L by 0.3. This is derivative, no derivative controller value we have to observe here. But when you have to use the PID controller part, it is also changes in three different controller part. Proportional controller part, that is 1.2 into T by L, and in the integral part, that is a TI, that is a reset time per pass, that is 2 into L, okay, that is a time 2 into time delay, and derivative controller part, that is 0.5 into time delay part. L is the time delay time, and T is the basically use time constant. Okay, so remember these tables also for the first method of Zigler-Nichols tuning controller part. Next, so here we have to use this another second method. Sorry, just wait. We have to use as the second method of this Zigler-Nichols method. So there is a one diagram we have to consider here. So all of you know, so this is a starting point, that is the input point we have to here also attach in the summing point. Then proportional controller we have to attach. Then plant or process we have to attach. Then the output from calculated from here. And it is also a starting a closed loop control system. So all of you know, every PID controller part, 90% of our industries we have to use this closed loop operations part with the help of that is PID controller part. So this Zigler-Nichols tuning method, it starts with a closed loop system with a proportional controller part, that is KP, we have to know. So it is first begin, it is the value of the low value of the gain, that is KP is here first starting point, that is low value. And here potential of this method, it is to go the unstable or cause the damage, because we know that in that case when you have to uses this proportional controller part, its ratio, the delay time and time constant part, that is time constant divided by delay time. So this case, this is basically potential for the in this method, it is very unstable, or anything is you have to long time it is not usable because it is damaged these controller parts also. Okay, next method. So these are the basically graphically we have to response here also. Okay, it begins with a low or zero value gain of the KP. So here you can see these are the basically delay time operations. So that's why no value we have to calculate it from this zero to the these positions also. This position it is called the delay time, that is L. And then it is also steady state we have to result sinusoidal curve in the sustained oscillations part in the periodic particular period we have to attach. So here you can see this peak to peak value we have to consult, that is also microsecond, millisecond, or second, something like that. So this is represent here also PCR. Okay, this is peak to peak value of this certain value of the proportional controller part, that is a gain of the proportional controller part. Okay, this is positive regions and this is the negative regions we have to consider for here. Okay, it is clear all of you?
Yes, sir.
Sir.
Okay, again this value it is coming after the gain you have to calculate the different gain in the different controller part. Okay, so that is KP, proportional controller, integral controller, derivative controller part. So after you have to apply this method, you have to calculate the different the value, the output value, that is a gain value of the different value, that is proportional controllers, its value 0.5 KCR. That is the gain of the proportional controller part after the tuning of the PID controller part using the Zigler Nichols method. So and so on. This is proportional integral part and this is PID controller part. Okay. So when you have to solve the any mathematical problems, so this value it is also calculated from here, these tables also. This is very helpful. Next, so in the corresponding of this method, this tuning method, it is basically determine an initial and estimated set of working in the PID controller part is an unknown systems also. So when you have to use this Zigler-Nichols tuning method, it is determined initial or estimated set of the working culture of the PID parameters for an unknown systems also, and it is usually included with the industrial process controller parts to motor controller as part of the setup utilities. So when you have to use this Zigler-Nichols method, so when you have to use different controller parts, that means proportional, integral or PID controller part, and also any speed control in a motor controller parts. Okay, so in that case we have to use. Okay, so we have to cover this tuning of this controller part. Okay, so this Zigler-Nichols tuning methods, these parameters will typically give you a response with an overshoot on the order of the 25% of good settling times. So these are the basically conditions when you have to apply the Zigler-Nichols controller method. And we may then start fine tuning the controller using these basic rules that relate each other parameters of the response of the characteristics. Okay. So these are the basically conditions we have to use this method in our proportional integral controller parts also. So this controller part we have to use this in our another three parts of controller part, that is cascade control system, feed forward control systems, and another one is the ratio control systems. Okay, so just recalls once again what is the tuning and why it is required, and what is the basic parameters we have to follow in PID controller systems. Okay, and what is Zigler-Nichols method. So these are the two things we have to follow this Zigler-Nichols method. First one, it is relationship between the three types of controller part, KP, KI, and KD. It is important response characteristics, which is basically rules you have to follow these three. Using this proportional controller part, that is KP, it is decrease the rise times also. Okay. Number two, using derivative controller, it is reduce the overshoot error and settling times, it is reduced. And when you have to use this integral part, that is Ki, it is eliminate the steady state error. Any steady state error it is coming in this PID controller part, which is eliminate this integral controller part. So this first rules or review we have to follow this method, this Zigler-Nichols tuning methods. Number two, this is another rules. It is good initial estimate for the parameters. So that's why it is not any difficulty in working in any process industries. So these Zigler-Nichols tuning rules or reaction curve method we have to use it in our different process control industries for good initial estimate for the parameters also. Okay, so after this tuning part, we have to apply in our different controller part. This is cascade control system, feed forward control system, ratio control system, and so on. So there are lots of control system, that is a controller part we have to apply. Okay, this is cascade control system. Okay, feed forward control system, another one feed forward feedback control system, and ratio control system. So, and next class we have to discuss, that is cascade control system, and so on. This process is continuing. Okay, so this is clear, all of you. So this is basically Zigler Nichols tuning method of a PID controller parts. Anyone any questions? So please ask me in this part. Everyone write your own name and roll number in the chat box also. And Vijit, you take a screenshot. Okay, anyone any questions? So please ask me. Okay. So next, we have discussed next class, that is cascade control systems. Okay. So just little bit introduction we have to cover. So in this control systems, when we have to use any closed loop control system, we have to use different types of controllability process we have to apply. Okay. So this single loop feedback control systems, it configures, it involves one measurement, that means the output purpose, and another one is the manipulated variable we have to use in our input operations. So systems with these different types of classifications, we have to depend the using the different controller parts, we have to classify it. First, cascade control system, another one feed forward control system, number three, feed forward feedback control system. Another one is the ratio control systems. Okay, so in this lessons, we have to discuss several special control structures. These are commonly used in our process control industries. And okay, we shall conclude this part of these three major structures. First one, cascade control systems. Then we have to discuss another feed forward control system. And number third, that is a ratio control systems. Okay, so this cascade control systems, it has one manipulated variable and more than one measurement systems. So please remember these first terms in this cascade control system. So when you have to uses when in control system there is a block diagram or signal flow graph. So in the block diagram, you can see there are lots of components are we have to use it. That is different blocks. That is G1, G2, G3, G4, and so on. We have to use this lots of summing point. Okay, we have to use this lots of takeoff point, and we have to use this feedback network. So each and every block or summing point, something like that, it is also cascading system in one controller part. So this cascade control system, it has one manipulated variable and more than one measurement is available. So it is an alternative to the considered if direct feedback control using this primary variable is not satisfactory and the secondary variable it measurement is available. Okay, so these are little bit changes or control we have to uses in different example purpose, that is upstream stream pressure, that is steam flow of the any turbine or steam flow of the any boiler systems. In that case we have to use is these cascade control systems. So this cascade control system, it uses the output of the primary controller to manipulate the set point of the secondary controller. So in this cascade controller part, it has a number of control systems we have to apply. So in this block diagram, just you can see little bit idea is clear. So this is a heat exchanger systems. Okay, so this is a basically heat chamber. Okay, and here two inlet value, two inlet systems we have to run here. First one, that is water inlet, that is a cold water, that is a normal water we have to input it here also. And another one, that is steam inlet, that is a one certain temperature we have to select it from the setting point. This steam, it is heated, this water in this we have to control this steam inlet, that is using this valve also. So this is a steam channel. Okay, so using this channel we have to follow the steam in this inlet to the outlet system. This is a steam outlet system. And another one, that is a water inlet, we have to normal water or cold water we have to apply from these chambers also. Okay, so using this steam line, it is also this water, it is also heated, and we have to setting these temperatures. Okay, these are the basically controlled by the temperature of the setting point. So this is a basically one set point where user or automatic control system which is set the particular desired temperatures value, and this temperature is maintained by this temperature controller part. And this temperature measurement we have to use as thermocouples, and these are the basically outlet of the water channel. This is the water outlet. So when user it is setting this temperature, then the desired temperature is matched to the setting temperature, then the water is outlet from here. So this is basically system for the example for the cascade systems also. Okay, so these are the basic block diagram which is included in this cascade control system. Here you can see same heat exchanger systems. This is two inlet part. One is water inlet, another one is the steam inlet part. Two output system, that is water outlet, another one is the steam outlet. But here you can see this is this channel. It is this input and output channel. It is slightly also thickness. That is a difference between the length. Okay, this is upstream. That is the up level of the tank, and this is also lower level of the tanks. And here also you can see steam inlet outer part, this is also outer part, this is length of the decrease from the starting point, that is the inlet part also. Okay, so why it is called this cascade system? Because you can uses the automatic systems. Here you can see this is a valve, which is this valve which is control the steam temperature of the in steam inlet temperatures. Okay, and one flow meter we have to uses from here, which is connected for the one flow control systems. This flow control system which is control the steam flow. Okay, and this steam flow which is connected another temperature controller set point value. This is a temperature controller set point. That means user, it is set from here desired temperatures. Then this temperature it is senses by these thermocouples. Then the output of the water outlet from here we have to use this in the different applications also. Okay, so this system it is called the cascade systems also. It is clear all of you?
Yes, sir.
So this is a very important topics, this cascade control system. Okay, one question it is also coming in this three control part we have to discuss day by day. First one, cascade control system. Number two, feed forward control system, and ratio control system. In these three control system, one question is also coming in your semester purpose. Okay. So there are lots of features are present in these cascade control systems. Okay. So first we have to know this outer controller part, that means outlet of the steam outlet or a water outlet, it has a control by the one master controller or primary controller part. In the same way, this inner controller, it is otherwise it is also named in the uh, either primary controller and secondary controller. Another one is the master or slave controller. This master and slave, all of you known in the digital electronics part, that is JK flip flop, that is a master slave flip flop. So this cascade systems, it is also uses, first one is the primary or secondary or master or slave controllers first. First one, first property, what is the property of this cascade control systems? Okay, first we have to uses this cascade control systems in this primary controller part. Here you can see this is a one examples we have to use as temperature sensors also. Okay, this is a block diagram. Using this we have to use these examples, that is a heat exchanger part. So in that case we have to draw the block diagram. Here you can see this is the input where we have to use as the setting the temperature part. Then two controller we have to use as here. One is the primary controller part, another one is the secondary controller part. Okay, so this primary controller part, it is connected one first set temperature, setting the temperatures also. Then it is another summing point we have to attach using this secondary controller parts, that is a flow of the water valve, that is a water flow. Okay, so in this examples here you can see you have to control the two systems. That means one is the steam flow control system, another one is the water flow control system. So that's why we have to use this primary control. Sorry for that, network is slightly disturbed from my head. Okay, so this secondary controller part we have to use is the control of the liquid, that is the flow of the liquid also. Okay, another one here you can see one flow meter we have to use is using this valve according to the summing point. Okay, this flow meter which is control the flow of the liquid in the liquid control systems also. Okay, so this is basically inner loop, that is the inner loop disturbance we have to consider from here. Another one, heat exchanger, which is heat the liquid or any water or any liquid you have to use this is heat exchanger, that is the outer loop disturbance we have to apply from here. And then finally it is one closed loop systems we have to attach, that is a temperature sensor, that is the outer loop we have to use this outer loop, that means the temperature sensors which is senses the temperature level of this flow control of the uh, output of the flow, that is output of the liquid. So the desired temperature, it is same to same in the setting of the temperature, then the output is coming from here. So this is basically one block diagram of the cascade control systems. Okay, it is clear all of you?
Yes, sir.